So yeah, welcome everyone. This is actually the very beginning, the very first lecture this year's Frontier Condensed Matter Physics Seminar between myself and Tomo Yumura. And then we wanted to sort of focus this series on sort of correlated electron sort of materials, and then a different type of measurement. And this week we're very happy to have Ming Yi to give the first talk. The first announcement was wrong, was made wrong by my student. Yeah. So she will be talking about the electronic orders in correlated Kagome metal. And next week we're gonna have a talk by a person at the IOPCAS, and he will discuss his most recent funding on the nickel-based nickelate superconductor under pressure, the bulk superconductivity, and there's a Nature paper associated with it. And then the following week we'll have a talk by Youngbai Kim. He's going to talk about the quantum spin ice. Yeah. So okay, Ming, it's all yours.
Okay. Thank you very much, Pengcheng. It sounds like I've I'm very privileged to start off this series, and I'm also very grateful for this opportunity for all of you for coming to hear me tell you a little bit about our experimental explorations into the regime of correlated Kagome metals. So let me motivate this talk via the following slide. Sorry. Okay, so as a motivation, we're very interested in looking for quantum materials that exhibit flat electronic bands. And as we know that there are two relevant energy scales in this problem, and it's the Coulomb interaction U compared with the bandwidth or kinetic energy of the electrons W. So because there are two energy scales, there are two extreme ways of getting into the flat band regime, and please feel free to interrupt me as I go on. So I just show you some properties of these two limits. So this is a very nice paper summarized here by Nicolas Regnault et al. So in one limit, we can consider one way to get into the flat band regime is by cranking up the Coulomb interaction U. What you will end up getting are these flat atomic bands. So in essence, these are atomically localized wave functions that have no overlap between different sites. And so this is a different object than the one on the right-hand side, which is the other extreme limits of achieving flat band, which is by reducing W relative to U. And so in the recent years, there's been a lot of activities in this regime. And I just want to show this comparison because these look like fundamentally very different objects. So on the right-hand side, these types of flat bands are topological flat bands. And the distinction is that instead of having atomically localized wave functions, here the block wave functions are extended. There is overlap, and they don't sit on the atomic sites. They sit in between the sites. And here, the hopping, the kinetic energy term is really quenched by this destructive interference due to the geometry of the lattice, right? So even though both these regimes gives us flat electronic bands, but they are very fundamentally distinct objects. And as somebody who uses spectroscopy, I just wanted to show you some examples of the distinction of these two limits. So first on the left-hand side, and this is the direction which we're very familiar with for the past few decades. A very good example of this is the heavy fermion systems. And here we know that we have these localized F electrons. When they don't interact with the conduction electrons, then you don't really see them from spectroscopy perspective. So what you end up seeing is that just these dispersive bands, with a smaller Fermi surface. And then only when you turn on interaction between these local moments and these conduction electrons, such as by the Coulomb interactions, do you start to see some spectral weight from these localized local moments. So for example, here you will see a flat band hybridized with this dispersive state, and then giving you a different Fermi surface, for example. Right, so this is something we're very familiar with, and I also want to give you an alternative example, which is something that's quite close to my heart, and also I think maybe a milder version of the heavy fermion example. So here, what I'm showing you is a multi-orbital system in the iron tricotinite materials. So here we have iron trichartonites, iron tellurium. You can replace some of the tellurium by selenium, and then you can map up a whole phase diagram. And what's interesting here is that from photoemission, you can see multiple hole bands around the gamma point. And you can see that there are 3 of them, and the inner 2, their curvature, which is related to the effective mass, don't change very much as you go from one end to the other. But there are another hole band here, where you can visibly see its bandwidth is being normalized as you go across this phase diagram, right? So we understand this as a orbital dependent correlation effect, and this is really the effect of going to the limit of large U. So we can see the mass enhancement of this particular band, which is shown here. This is XY orbital. You can see its mass enhancement compared to the effective mass from the DFT calculation actually tends to diverge as you reach iron tellurium, and while other bands remain with a constant mass enhancement. So theoretically, this is understood in this picture by this slave spin calculation by Timel and Rongyu, and what they have seen is that here in a multi-orbital system, in a strongly correlated metallic regime, you have dispersive bands with wide bandwidth, but you also have this extremely renormalized flat band, which is hybridizing with the rest of the dispersive states. And here, very clearly, you can see that this almost flat band has, the more flat it gets, the less quasi-particle coherence it has. And then in the extreme limit, where that orbital becomes not localized, then becomes completely flat at the Fermi level, and then loses all of the quasi-particle coherence, right? So these are the, just want to show you some key properties of the flat bands from this correlation-induced limit. Okay, so the other thing we can observe is that as this band becomes not localized, you also will have a change in the Fermi surface in the absence of any symmetry breaking orders. And that's also experimentally observed by looking at the change in the Fermi surface as we measure from RPES, right? So this is just an example of the left-hand side way of creating flat bands in this atomic flat atomic band limit. So I want to show you some contrast in the right-hand side. And this is the direction where you can have the quenching of the kinetic energy by the destructive interference of the lattice, right? So this is where I think the community is now very familiar with these examples. The Kagome lattice is the most commonly occurring lattice motif amongst the materials that we have, where you have this destructive interference of the electronic wave function. So there's a plus and minus in these destructive interference such that there's no hopping allowed outside of these hexagons. So in momentum space, what this means is that this object, this compact localized state, becomes this flat dispersion with 0 bandwidth. And this is, of course, idealizing this tight binding calculation with nearest neighbor hopping. And the distinction is that as realized in a real material, this is the really nice work by Ricardo Comin and Joe Czukowski's group. You can see that in cobalt tin, you can clearly see the full quasi-particle coherence of these flat bands made by these destructive interference of the hopping, right? So this is in contrast to what we know about the correlative interaction-driven flat bands. So here's the distinction between the two. Just to give you what I want to really emphasize is that even though these are fundamentally different objects, but there is this really nice analogy between the two limits, and this has really led to a lot of theoretical activities in mapping one onto the other as a way to look at these correlated topological systems. So here I show you just 2 examples. This is, of course, not there are more than what I've listed here, but these are some constructs from theory perspective of how to map one onto the other. So this left-hand side is Timel's group's result, where they've taken together the topological flat band, which has this touching with the dispersive states as a group, as what they call the compact molecular orbitals, and take this as an object which they can then linearize and then map this onto the Kondo heavy fermion problem. So on the right-hand side, this is another construct by Zhida Song and also Andrei Brnovik, where they've treated this problem for twisted bilayer graphene, where they recognize that even though there's a topological touching at the gamma point between the flat band and also the dispersive Dirac points, what they can recognize is that the flat band has over 90% that can be localized, made this analogy to the local moments in this heavy fermion model, in addition to the dispersive states. So in this mapping, they can then also map this onto this topological heavy fermion model. So I just want to mention this because there is a value in thinking about the mapping of these two limits of creating flat bands and try to understand what a more interesting physics we can actually carry over from the heavy fermion problem onto the topological flat band problems. So as a way to motivate this, just as maybe one more slide of the motivation is that we know that these are compact localized states. These are objects that are real. You can see them, and this is the example of an STM work from Berthold Jack's group at Hong Kong University of Science and Technology, and using STM, they've made the spatial mapping of the Kagome cobalt-tin material. So basically, in cobalt-tin, you know that the flat band lies at certain energies, and what they do is that they can do a mapping with STS, and that they tune their energy to be at locations where the flat bands, the topological flat bands lie. They can actually see these compact localized states just as predicted in the middle of these hexagons. And if they tune their energy to be away where the dispersive states are, then these are right. They go on to along the bonds, right? So these are real objects, and then the question is, these are objects that are distinct from the itinerary electrons that we know, and they're also distinct from the local moments that we know. So the question is, what do we think about these objects? Are they itinerant? Are they local? I'm sorry. Are they, so can they, in real materials, can these objects participate in the forming of electronic orders? Should we think of them, as something that can be tuned between the itinerant limit to the local moment limit? If so, in a real system, what controls this degree of itinerancy versus local moment? How do we understand this problem? I think this is fundamentally a very interesting problem. It's a very fundamental, as far as I understand, to the correlated topology problem, because right, so topological flat bands have this touching point which you cannot really easily gap out. So then this is really a question: how do we understand how these states contribute to the formation of electronic orders? So we've seen these are important in Moiré systems in the formation of these mini flat bands, and I think in some of these twisted bilayers graphene systems, there's already been evidence of unconventional normal state properties, such as I learned this about cascades, and so on and so forth, that suggests that correlation effects cannot be ignored. While we haven't gotten to the point where we can understand or probe with the spectroscopy for these Moiré systems, what I hope to tell you a little bit about is what we have learned among bulk materials where they are more accessible to tools such as photoemission, STM, inelastic neutron scattering, and so on and so forth. And how do we start to look at what we can learn from these objects? So that's what I'm tell you about for the rest of the talk, and I'm going to largely show you two projects that we've recently worked on. One is the Kagome magnet iron tin system, and then the second half will be about this chromium-based Kagome system, which we recently worked on together with Pengcheng's group. So that's the rest of the talk. Let me see, how am I doing on time? Okay, so as a way to introduce maybe in a more complete picture, besides the flat band, we also know that intrinsic to any Kagome lattice system, there are a total of 3 key signatures in the electronic structure that are to be expected. So the first one is the flat band, which we've sort of talked about already. And you can imagine that if we tune our chemical potential to be in the flat band, this will give us a large density of states, and then at least one of the competing ground states will be a form of a Stoner type itinerant ferromagnetic order to be expected. The second key signature of a Kagome lattice is a Dirac cone at the K point of the baryon zone. And if you consider the effect of spin orbit coupling, this will gap this Dirac point. And then there will be finite barrier curvature, which will give you anomalous Hall. So if you tune your chemical potential to be in the gap, then you should expect to see also anomalous Hall. The third one, which is very famous and also familiar to this audience, is a pair of Van Hove singularities. And these are the saddle points and the band dispersions, which we know in 2D will have a divergent density of states. And the key expectation is that if we tune our chemical potential to be at one of these Van Hove singularities, then the Fermi surface, or the idealized Fermi surface, will look like this perfect hexagon. And as we know that there will be this nesting vector, actually 3 of them, that will give you a natural instability towards a 2x2 charge density wave order. So given any bulk Kagome material, these are the 3 things we can look for. And very directly, there are expected theoretical expectations of what kind of emergent orders are to be expected. Because of these, there's been a lot of activities in the past couple of years trying to look at different bulk materials that exhibit some sort of Kagome sublattice. And this is by no means a complete listing, but I wanted to organize this in a way that connects back to these signatures in the electronic structure. So we've seen there's a discovery of superconductivity, charge density wave, and also magnetic orders amongst the various Kagome systems, and also highlighted in red the element that gives rise to the Kagome lattice, right? So as you look across these systems, you realize they actually span this, basically this entire row of transition metals. And what does this tune? So in bulk materials, this gives us a way to tune across the chemical potential across these signatures. And then at the same time, there's also a bit of tunability in terms of the strength of the electron-electron correlation effects, right? So we can somewhat organize this by showing you some examples, 3 examples of the DFT calculations for 3 members. If you don't enjoy looking at spaghetti plots, I will also put on top basically where this type binding calculation largely falls together with where the Fermi level is for each of these 3. So if you start from the upper right corner, this is the vanadium based Kagome system, 135 system. And here you can clearly see that a bunch of Van Hove singularities happen to be at the Fermi level. And as we know that there's been a lot of very interesting effort studying the charge density wave orders associated with these materials. If you go down, this is what I'm showing you is the DFT calculation for the non-magnetic normal state of iron tin. And if you look at this, these are the topological, Kagome topological flat bands, and they're right at the Fermi level, right? And these also, the iron-based, also the manganese-based systems are the ones where we have the magnetic order. And then this third one on the left-hand side, this most newest member of this family, which is a chromium-based system. And you can see that the location of the flat band is somewhere in between these 2. It is much closer to the Fermi level, but not quite yet there, according to DFT at least. So this last number, I put it into the middle of the circle because in this phase diagram, as I will discuss later in this talk, there's a discovery of superconductivity, charge density wave, and also magnetic order. So this is perhaps the most complex and interesting of them all. Anyway, so I'm going to talk about, in order, first the iron tin, and use that as the example to look at what could potentially be the origin or nature of the magnetic order in this corner of this map. Okay. All right. So iron tin. Iron tin is arguably probably the simplest, structurally the simplest Kagome bulk material that we know. It is made of iron as the Kagome layer, and in between the layer there's tin, and also as well as tin within the Kagome layer. And it's been known that below a temperature about 366 Kelvin, the system prefers to order into this A-type AFM order. So within each layer, within each Kagome sheet, the moments are ferromagnetic and then they are flipped. They're anti-aligned as you go in the stacking direction, right? And this is the only order that is known in this compound, which makes it maybe a very nice system for looking into the nature of the magnetic order for this Kagome system. So in bulk single crystal form, this is the transition temperature. And there's been a lot of studies, more than one, on the RPS aspect of what the bands are for single crystals. And if you want to answer the question of the role of the flat band in the magnetic order, what we really need to do is to experimentally study the evolution of the band dispersions across the ordering temperature. But it turns out that for single crystals, practically it's very difficult to do that, as the sample will almost always die before you get there. So it's actually, there's not been a good way to study this transition in single crystalline form. So our approach is slightly different. I just want to, so my excellent postdoc, Zhengren here, came to our group and built this MBE system attached to our RPS system, and he was able to, together with my student Ananya, grow iron-tin thin films. And it turns out that surprisingly, these thin films are quite robust. The surface can, survive as we ramp up the temperature to 400K and then back down, and then all the features are robust. So this gives us a platform to study the nature of the magnetic order in this Kagome magnet. Okay, so just some practical numbers. This is a really basically bulk-like thin film, 60 unicells, and then the transition temperature is very similar to single crystal. And this is kind of Fermi surface maps we can take directly in situ. Okay, so before I show you the actual data, which shows you the nature of the magnetic order, let me just put in the slide to discuss a little bit about what we should expect. So as we know that there are two extreme limits of understanding the nature of magnetic order in quantum materials. In one limit, we can have the Stoner type, which is really a large density of states at the Fermi level will spontaneously split into spin up, spin down bands, and this will generate the magnetization. So what one would expect is that you should see a splitting of the band really happening exactly at the Curie temperature. On the other limit, the Heisenberg limit, here you will have the local moments, but the distinction is that even though you have exchange splitting, but the local moments themselves should not disappear at the Curie temperature. They should persist well above the Curie temperature. It's really the correlation between the local moments that disappears at the ordering temperature. So in essence, what are you going to see if you do photoemission on this? You should see that the exchange splitting should remain more or less the same across the ordering temperature, across the Curie temperature, but it's just a spin polarization within each band should disappear. Right, so very clearly, there's a straightforward way to look at, how, which side of this, this nature of the magnetic order, which side we're on, just by following the band evolution across the ordering temperature. So to put this into context, let's find the simplest example. So people have done this routinely for magnets, and so here's an example. Photoemission measurements on iron film grown on copper 001 surface. So what you see here on this plot, there are two curves. You have these white markers. These are the measurement of the spin polarization within the band. And you can see that where this disappears, this marks the ordering temperature, the Curie temperature. And then you also have this blue dots. The blue dots is the measurement of this exchange splitting, of the spin splitting as a function of temperature. So what you see that is that this splitting actually does not disappear at the ordering temperature, but it actually persists to a much higher temperature. So even for iron films, which maybe people tend to think of them as itinerant magnets, they actually have, they're not completely Stoner type. It's actually quite rare to find systems that are completely Stoner. You still have a large portion of this exchange splitting persisting at higher temperature. But you can see that this is the one way to sort of gauge which side of this scale we're on. Okay, so with that said, let me show you our what we have learned from iron tin. So before I even show you the data, I just want to roughly give a give us sort of like a schematic understanding of what we should expect from DFT perspective, which we collaborate with Ming Yi and also Heng Tan. So essentially, if you think about iron tin, each layer is ferromagnetic. What that means is that for each layer, there should be a splitting into the spin minority and also a spin majority bands as you go right in the magnetic order phase. And this is actually largely captured qualitatively in the DFT calculations. So when they calculate the density of states for the non-magnetic state, you see a large peak at the Fermi level, and this actually, very nicely matches with the Kagome flatband in this DFT calculation, right? And then in the AFM order phase, this peak splits into two. And when they look at the projected bands into the spin minority and spin majority states for each layer, they can indeed see that these peaks corresponds one of them to the Kagome flatbands for the spin minority states, and then the other one below the Fermi level corresponds to the spin majority Kagome flatbands. So the energy difference between these two is essentially the exchange splitting. Okay, so therefore we can utilize this picture and track as a function of temperature the evolution of these bands through the ordering temperature to get a sense of how local or how itinerant the system is. And so to make a long story short, we can first look at the band dispersions measured along high symmetry directions. And you can see that there's actually this peak in the density states about 1 eV below the Fermi level. And this actually matches relatively well with the DFT calculation for where one should expect the flat bands in the spin majority states, right? So that means the DFT calculation for the exchange splitting should be roughly correct, at least comparable to what we observed experimentally. The next thing to do is to ramp temperature. And so we got to find pieces of the band that correspond to the spin majority states and the other pieces of the bands that correspond to spin minority states. So if you look over here, this is like a ramping up in temperature of these bands. And I hope you can sort of see that for the spin majority states, as you ramp up temperature, they move up in energy. And that's consistent with their nature as spin majority states. And then in the opposite side, the spin minority states shift down as you ramp up temperature. So we have indeed captured regions where we can see these are spin minority, spin majority states. Even though the shift, but if you look at the total amount of the shift in energy, you will notice that for this piece of band, it only shifts by about 20 millivolts. And that is like a tiny fraction of the overall exchange splitting expected from DFT. And this one as well. So thinking back to the picture between the Stoner type and the Heisenberg type, we can see that for iron tin, as we go across the ordering temperature, only a small fraction of the total exchange splitting actually closes. So what this suggests to us is that the iron tin, even though the topological flat bands at the Fermi level, it really falls more in line with the local moment picture over here. Right, so this is and these topological flat bands are associated with the compact molecular orbitals that we have discussed previously. So this is the first part, and I just want to take a pause to thank all the collaborators for this. I just really want to acknowledge Zheng, who's the one who really led this work, and also Ming Yi and Heng Xin for the DFT calculations, and Lei Chen and Qimel for a lot of the theoretical discussions about these compact molecular orbitals, and these are all the rest of our collaborators for this project. Okay, good. So this gives me some time to discuss the second portion, which is also unpublished data, and that is this most recent development of this chromium-based Kagome system. So let me introduce this compound a little bit. For those not quite familiar with this one yet. So the original paper is cited here, and they have successfully made this isostructural material to the vanadium-135. So everything is exactly the same, except they have replaced the vanadium with chromium. So chromium here is the Kagome lattice. And what's really interesting about this compound is that at ambient pressure, there are symmetry breaking electronic orders that they have found. And then as a function of hydrostatic pressure, they see this phase diagram that really looks like what we're familiar with in terms of unconventional superconductors. So you see a suppression of the competing electronic orders, and then when they're suppressed, then you see the emergence of the superconducting dome. So this is really exciting development, and I'm going to show you some more details about this material. Okay. So let me first talk about ambient pressure. So this is what, again, I'm just showing you results that's already reported here. So if you look at the resistivity measurement, you can see that there is an anomaly at 55 Kelvin. This anomaly is also seen in the heat capacity measurement here. You can see that the in-plane resistivity and the out-plane resistivity are quite different. So this is somewhat two-dimensional. And then the value of the resistivity is on the order of milliohm centimeter. What's also very interesting is that from the heat capacity measurement, they can extrapolate the Sommerfeld coefficient to be 105 millijoules per Kelvin mole, which is relatively, I think it's reasonably large, and as the authors point out, this is 4 times larger than the value for the vanadium version of this material, which all of this starts to suggest that this is perhaps in the bad metal regime. Now, about the order. So here, what's interesting is that the authors report 2 types of electronic orders that occur simultaneously at 55 Kelvin. First of all, the magnetic susceptibility has a drop at 55 Kelvin. And also, this is more recent development, they have carried out NMR measurements. What they see is that there is a splitting in the NMR line as you go across the ordering temperature. And they also, from what I understand, discussed that this line width is broadened, which is more compatible with AFM type of magnetic order than ferromagnetic order. So this suggests that at least one of the transitions here is the magnetic order. At the same time, they also carried out single crystal X-ray diffraction measurements across the ordering temperature. And here is a comparison of high temperature and also low temperature. And you can see that there's these superlattice peaks, and they figured out that this is really indicating a charge order that has a Q vector of 1/4 Right, so at ambient pressure, as far as they can tell, these 2 transitions occur simultaneously at 55 Kelvin. Now, when they put this crystal under hydrostatic pressure, first of all, they see the single transition is suppressed, and at the same time, split into 2 transitions. And so they read this as, very much like the iron nictide type of phase diagram, where you have a lattice component, also a magnetic order. They separate under pressure. And then as these transitions are suppressed, then eventually they see signatures of superconductivity with a maximum TC of about 6 Kelvin here at the top of the dome. The third interesting thing they have also pointed out is that if they look at the resistivity parallel behavior, they can fit the alpha, which is the resistivity goes like T to the alpha, and they can see that in this region of the phase diagram, this is roughly in the regime of a T-linear behavior. And you can see that this looks very much like the phase diagrams that we are familiar with for a quantum critical point that emanates out of this quantum critical point, right? So excitingly, this kind of phase diagram is very at least it looks familiar to those who work on the unconventional superconductors. Okay, so this is what we already know from this paper, and then now I'm going to show you some of the experimental results we have obtained in understanding some of this phenomenology in this material. So I really want to acknowledge, so these are crystals grown by Zihao Wang, who's a student in Peng Chun's group, and he worked very hard in growing large enough crystals for all of us to measure. So this is an example of a large single crystal he grew, a couple millimeters large. And they've also carried out X-ray diffraction to confirm that here, as you go below the ordering temperature, you see the superlattice peaks occurring at these like consistent with the 1/4 superlattice seen in the original paper. So with these crystals, we now have access to starting to think about what are the electronic structures of this material. For the photoemission measurements, these are all carried out by by my excellent student Yu Cheng Guo here, who really tried very much measuring different pieces of the crystal and then find ones that actually can give reasonable band dispersions. So if you compare the chromium-based Kagome lattice system to the vanadium-based system, you can already see that at the DFT level, there is a the flat bands are much closer to the Fermi level, at least, but still above the Fermi level, right? So this is the flat band density state peak. You can see. So if we look at the Fermi surface mapping, which is shown here, we see two main features. One is this large electron pocket at the gamma point. This is the calculated Fermi surface. And then in addition, we see these features at the endpoint of the Brilliant zone, which roughly matches with these pockets. Not quite resolved, but they at least suggest that on a large energy scale, the DFT does a reasonably okay job. So here, if we were to look for the Van Hove singularities for the chromium-based system, we have to go down by half EV below the Fermi level. So here is the constant energy contour, about half EV below, where you can start to see these, typical corner sharing triangles that's reminiscent of what you expect when your chemical potential is tuned to the Van Hove singularity. Okay, so it seems like on a large energy scale, DFT is actually doing a reasonable job of telling us what's happening in this material. We can learn a bit more if we look at the measured dispersions. So this looks like a very busy plot, but the key message is the following. So what we have chosen to work with are these site-dependent local coordinates, a way of defining the orbitals. And the benefit of this is that in this way of defining the orbitals, they fully respect the lattice symmetry. So we can actually utilize these orbitals and compare directly to our photoemission measurements by considering the selection rules from the matrix element effects by playing with the light polarizations. So we can look at, for certain cuts, high symmetric cuts, if we use a certain polarization, which orbitals are even, which orbitals are odd, and which ones can we see, which ones we cannot see. So by doing all of this detailed analysis, which I'm not gonna tell you about, so Yu Cheng actually worked out all of these this table of different cuts and different polarizations, which orbitals are actually we can actually observe, and then what he did is that he then for each of these cuts, he plotted on top those orbitals that you can actually observe for each of these polarization setups. And so if you zoom out and if you stand far away, you can sort of see there's a reasonable agreement between calculation and what we see. So for example, there are these features which you can see a reasonable agreement on this 6 eV energy scale. And I just also want to point out in this way of seeing, you can see the Kagome flat bands to be dominated by the XZ, YZ, and also the X squared minus Y squared orbitals. These are the three that mainly dominate the peaks above the Fermi level that are associated with these flat bands, right? Okay. What about smaller energy scales? So I'm gonna then zoom in to about a EV around the Fermi level and show you what we see there. So if we zoom into that energy regime, and what we can see is that if you look at these energy distribution curves, for every single cut, we can see a peak near the Fermi level, right? Especially, for example, this one is relatively clean cut where you can see fewer orbitals, and you can see that there's a peak which is really ubiquitous along this gamma m direction. If you don't quite trust this, I can show you one more evidence of this. For example, if we zoom in to this cut, which is across the gamma m direction, where you have this prominent p orbital from the antimony, and zoom in, which is shown here, you can see that within this pocket, this electron pocket, there is this very clear dispersion close to the Fermi level, right? You can also see this in these EDC stackings. So this is the electron band, which is shown here. And then this is the flat band, which you see here. What's the significance of this? If you compare this to the well-known vanadium version, you can see that In the vanadium version, there's very clean dispersion. There's no flat features around the Fermi level. There's nothing inside this electron band. And the significance of this is that if you zoom into the DFT calculations, you will notice that for the vanadium system, here is the electron band. Here are the flat bands, which are well above the Fermi level. For the chromium one, next band up above the electron band, this is where the Kagome flat bands are. And see, flat band is suggesting that what we're seeing here, hugging the Fermi level is actually these Kagome flat bands, which are somehow lower to below the Fermi level compared to what DFT has told us. Okay. Moreover, we can quantify where this flat band actually is. If you fit the dispersion like this, you will see that otherwise, if it was not there, you would see it like a straight dispersion. But you can see, like in this fitting, you can see that it deviates from where this flat band actually hybridizes with this electron band, right? We can use that as a way to look at the location of this flat band, and we can do that as a function temperature. So I'm showing you here is this fitting, and you can see this this kink. I really want to emphasize this kind of kink is not typical of what we normally call the electron boson coupling. This kind of kink here is really because of the dispersion hybridization between the flat band and the dispersive state, right? And so for a normal electron boson coupling, you will not see this kind of state here far away from the dispersion. But we can utilize the location of this as a way to track the location of the flat band. And what's interesting is that as you raise the temperature between 10K across the ordering temperature into 140K, you can see the location of this hybridization kink actually shifts towards the Fermi level. You see that actually in multiple cuts. And another way to see this is by looking at the EDC at a location where you can only see the flat band. And that is a peak right here. And as you warm up from 10K to 140K, you see the peak actually shifts towards the Fermi level, right? And we have also done thermal cycling to make sure the sample hasn't aged, hasn't died, hasn't done anything weird. And then when we cool back down to 10K, it recovers back to where the blue peak is, right? So we can done this systematically for a temperature as a function of temperature, and you can sort of, this is, give or take. You can argue perhaps it's consistent with the onset of this ordering temperature of 55 Kelvin. Okay, so this is a summary of what we have seen from our photoemission measurements. I also want to acknowledge independent work that we have also seen appear in the archive. And I think these are also excellent work. So there are two papers that we have seen. This is one from Junfeng He's group, where they have also measured this materials in photoemission. And I think from their Fermi surface, they see this large pocket of the gamma point. And I think they can also arguably see these flat band features very similar to our conclusions, right? And then this is another work is Lucian Yang's group, and they have seen very similar Fermi surface, and also evidence of these flat bands below the Fermi level. So in terms of where the flat band is in these materials, I think we have consistency between all three of our groups, which we all measure independent samples. So I think that's a good thing. Okay, so that's the photoemission part, and next, I want to show you some results from resonant inelastic X-ray scattering. And this is not my work. I'm presenting on behalf of Peng Cheng and Dijing Huang, but I just want to also, I think this for completeness, let me show you some of this recent results. Okay, so why do we want to use RIXS? As these samples are quite small, they are actually not very accessible by inelastic neutron scattering to look at magnetic excitations. And then it's plenty of work I've demonstrated that you can see spin excitations by choosing to use a cross polarization geometry. So these are some of the work done on cuprates and also nictides, where if you use your polarization in this pi geometry, then what you see are these spin flip excitations, right? So this is the work done on the cuprates, where you can look at the pi scattering geometry in comparison to sigma scattering geometry, and they have ascribed this to paramagnons in cuprates. This is another example in the iron nictides, where, again, using this pi cross polarization geometry, they can also see spin excitations in these barium 122 materials. So this is a very well established technique. And so again, this is the work of Peng Cheng and also Dijing Huang's work. I'm just talking about this on behalf of them. So they have measured RIXS on this using this cross polarization geometry in the pi channel. And they've measured this at the chromium L3 edge, and this is the X-ray absorption. These are the 5 energies they've measured this at. And to show you an example, here, what you see here is that this gray peak at the elastic line, this is what they measured with the sigma polarization. But in the pi polarization geometry, they see that there's this tail, which really cannot be ascribed, right? That means that there's additional spin excitations, which is not accounted for by what they see in the sigma polarization. So they can extract that component, which is shown here, and fit this with this damped harmonic oscillator model. And so this is the elastic peak with a known instrumentation resolution. And then beyond here, there are 2 features they can fit. And then here is this is basically how they can extract these spin excitations from the chromium L edge. Okay, so the first thing is momentum dependence or independence. So given the energy range that they have measured a portion of the reciprocal space. And you can see that in this way of fitting, the energy of this excitation actually is largely non-dispersive. There are 2 modes; they're largely non-dispersive, even though there's a small region of the reciprocal space. But this is largely consistent with the flat bands that we see from photoemission. Right. The second thing is temperature evolution. So they've measured this across the transition of 55 Kelvin. And again, they can fit these excitations by subtracting off the elastic peak. And you can compare across the ordering temperature. And what they notice is that there are 2 behaviors from the fitting of the 2 modes. What they see is that this damping factor actually increases as you go into the ordering temperature. And then at the same time, the energy, the central energy of these excitations also shifts away from the elastic peak, right? So this is actually very consistent for the 2 modes that they have extracted from this measurement, right? So because this is really pi geometry, so what they're seeing is really spin flip excitations here. And then one more thing to note is that the energy of these excitations is it's smaller than that of the cuprates and pnictides, which are in an energy range above 100 millivolts, maybe to 200 millivolts. But here, this is more like 70, 80 millivolts, right? Okay. So if we take the RPES data and the RIXS data together, we actually come to a reasonable interpretation and understanding of of what we're seeing across this ordering temperature. So here, we see that from the RPES measurement of the single particle spectral function, we see the flat band shift away from the Fermi level as you enter the ordered state. So if you think about in terms of the particle hole excitation, right? So this is sort of a schematic showing you what the single particle band dispersions look like. As you enter this order phase, the flat band shifts away from the Fermi level. So the excitation actually should gain a width. And this is actually very compatible, as far as we can understand, with the RIXS observation of the increase in both the gamma term and also the E0 term, right? So you can see that as you enter into the order phase, this both becomes broader because of the widening of this delta E, and also shifts away from the elastic line. So we think this is actually quite consistent, can be consistently understood as the spin flip electron hole excitations that arise from the flat bands near the Fermi level. Okay. Lastly, that's all the data. I wanted to also just talk a little bit about the connection, to potential connection to superconductivity, and just cover. So this is in the original paper. And so we know that when these order phases are suppressed, this is eventually where we see the superconductivity. And so from DFT perspective, what they see is that by going to 5 GPa, which is where the superconducting dome is maximized-ish, you can see there's actually quite a bit of tuning of the location of flat bands. We have to be careful because in experiments, we actually see the flat bands to be slightly below the Fermi level. So which direction the flat bands are shifted, it may have to be further understood. But at least this suggests that perhaps one way to think about this is it's conceivable that the presence of these flat bands near the Fermi level play some role in driving or inducing electronic orders, and which pushes the flat bands away from the Fermi level. And then when these order phases are suppressed by pressure, could these be leaving behind a larger residual density of states from the flat bands to the Fermi level that eventually could participate into the emergence of superconductivity? This is just speculation, and I think this is just something interesting to think about. So about this issue about of where the flat bands are, there's been a couple of work already in the literature trying to resolve these issues by looking to the effect of correlation. So this is again from my colleague Timel's group. What they have done is they've done this I think 9 orbital tight binding fit, and then using slave spin, they can incorporate correlation effects, and they indeed see a shift of the flat bands towards the Fermi level in the right direction, consistent with our observations. This is another effort of DFT plus DMFT calculations that again also shifts the flat bands towards the Fermi level, and I think it'll be as a this is a direction we need to understand for a better description of the low energy electronic states. Okay, I'm mostly done. I just want to summarize this last part for the work on the cesium chromium 3 antimony 5. So in summary, we have observed these electronic flat bands just below the Fermi level. This is in contrast to what is shown in the DFT calculations. And then from RIXS, there's also the observation of these electron hole excitations, which are associated with the flat bands. And then the very consistent observation of the temperature evolution of both of these features really suggests that these flat bands are participating in this ambient pressure electronic orders. I think as a community, maybe we should also think about in the future, the next step may be to understand this orbital selective correlation effects, and then which can more accurately describe low energy electronic states, including where the flat bands actually are. And then the next question, I think the burning question, is what exactly is the magnetic structure? And then the next step is to understand the origin of superconductivity for this Kagome flat band system under pressure. So and just acknowledgement for the second part. And so Yicheng is my student who did the RPS measurements. So Hao is the one who really worked on the large single crystals that enable all the work. It's from Pengcheng's group, and then the RIXS measurements with Dijing's group in Taiwan, and all the theory support from FeSn and also in Timel's group, and many other local and also external collaborators that we're very thankful for. So I think that's it. Thank you very much.
Thank you, Ming. A very nice talk. Any questions? Very nice summary. Yeah. Okay. Yeah. Let's Dan.
Hi, Dan.
Yes. Hi, Ming. Very beautiful. I want to ask you for the chromium compound. The question about the location of the flat band. If it's really below EF compared to above EF from DFT, Lunger's theorem should say all the other Fermi crossings should be different.
Yeah.
To account for that. Did you see the difference in the KF of the other bands, or do you have enough resolution to address that?
That's an excellent question. I don't think we can claim we have enough resolution to compare to that level. For example, the small pockets at the endpoint, we really can't compare them at the KF points yet. This is basically, like, I think we don't have, I don't think we have enough resolution to resolve the precise sides of the other pockets at that point. But I think you have a good point.
Okay.
There has to be some other adjustments of other bands that
there would have to be, exactly. Yeah. Okay, thank you.
I also have a question.
Okay.
Thanks for the nice talk. Is there, so you don't see any evidence of this? There was an archive on a spin density wave in this chromium compound.
We don't. We tried. So this was measured in the in the order phase. We don't see any folding, at least in the current stage. But maybe in the future, this could suggest one of two things. One is that with better improvement in sample quality, eventually we could see this. This is maybe perhaps like the scanning version, or it could be just intrinsic, which is that the folding potential of this charged water is weak enough that you don't see a drastic reconstruction of the Fermi surface. But we don't know which case it is yet.
I see. Thank you.
Yeah.
Yeah. Amir?
Yeah, very nice talk. I have a question regarding this Sommerfeld coefficient. Do you have an idea why it is much larger, 10 times you said larger than in the vanadium case? And why is it so high? It's actually quite high for a 3D metal.
I can speculate. I can speculate. So for one example is so according to DFT, the flat bands are actually not quite there at the Fermi level, but experimentally we actually see them to be much closer to the Fermi level. That could be one possibility. This is for the vanadium case, I think the DFT does actually a pretty good job at describing exactly where bands are. So I think for the chromium one, the fact that the flat bands are much closer to the Fermi level possibly could be a contribution to the larger Sommerfeld coefficient. That's just speculation on my part.
Okay. Yeah, I mean, by the way, I mean the magnetic order, I mean, has not been sorted out in this compound because the samples are still too small for neutron diffraction. Well, we're trying very hard. Wow, she gave a very clear talk. Yeah.
Sorry. Yeah, yeah, there's still.
No, it's actually excellent. The talk was very clear. Yeah.
Thank you. Thank you.
Yeah. Are there any other questions for her? Yeah, this is actually one of the sort of a first series of this compound, I believe, is the first compound has all three ingredients, right? Has the charge density wave and spin density wave potentially, and also superconductivity. So I mean, the only problem is the superconductivity under pressure, which is hard to study. Right. But even just understanding the sort of the zero pressure properties is going to be, very enlightening. I mean, as compared with iron germanium, which has charge density wave and magnetism, but no superconductivity, whereas vanadium stuff, which I personally believe is actually sort of BCS-like superconductor. So mostly people's interest is trying to understand the vanadium compound is to understand the origin of a charge density wave and how that couples with superconductivity. So this particular compound seemed to really impasses the sort of the three interesting magnetic and charge density wave and superconductivity properties in the same compound. And apparently you can dope it according to some people in China. And when you dope it, I mean, just after dinner conversation, they said that it can potentially be an insulator, but I haven't seen any posted paper on that yet. But people are working very hard. But the problem with this compound is extremely difficult to grow. We tried this for more than a year, so yeah.
I see. Yeah, but it's a worthwhile project to work on.
Yeah. Okay, if there's no more questions, that's
actually, I do have one question concerning the doping in particular. If it's yeah, so like how amenable is it necessarily to doping, and is this doping more in like the vanadium direction or in the other direction? Because if I remember correctly, I feel like doping from they
wouldn't tell me in sort of a detail, right? But they said typical doping wouldn't work. It wouldn't go in because this particular phase seems like it's the metastable phase, and what this means is that you cannot make a bulk powder out of a chemical reaction. You can only grow this through single crystal, through this flux method. And in terms of doping, I mean, the understanding is that you can they try all kinds of substitution, but it was the chromium side. You can substitute it with something else, another metal. I mean, they didn't want me to say any details, but once you substitute it, it can potentially become an insulator. Yeah, which I find quite interesting. Yeah.
I mean, and then generally. Oh, sorry.
The original paper is accepted for Nature. It will appear soon, I assume. Yeah. Sorry.
And then generally as well for these like, vanadium-based or even potentially this chromium-based, are they amenable at all to MBE type growth, or is there something preventing that?
I think Ming can better address that because I don't do MBE, so I'm not sure.
I guess this is a question more for Ming, yeah.
My Zheng does the growth. I really know nothing about MBE. I don't know, but if you can do chromium, what we have done is an iron-based systems. You guys been able to grow. I don't know about the chromium-based.
Yeah, but even in iron-based, I mean, Ming, you said it's hard to grow iron germanium, right? It's easy to grow iron tin, but iron germanium is quite hard, right?
Yeah, so I guess folks are still working on the recipe, but iron tin has been routinely made.
Thank you. Yeah, and the talk was very, very clear. It was very interesting to see. Thank you.
Yeah. Thank you all. Yeah.
Good to see you, Dan.